Welcome back. In this video, I hope to work through and kind of get us a summary of some of the relationships using entropy that we are going to talk about and use a lot through this chapter material. Okay, so let's think system, surroundings, and universe. So our number of microstates of our system is given by omega, which is the function of energy. And so S of the system, we don't give a subscript, is K log. KB log omega. The number and the system is this thing that we are interested in. The surroundings is the area around the system. And we often call that a reservoir because it turns out that subscripts S are really hard to distinguish because system and surroundings both start with S. And so we call the surroundings the reservoir. And so the entropy of the surroundings is given by the number of microstates of the surroundings. And the total number of microstates in the system and the surroundings is given by this total, or the universe. And so S total is the same thing as S universe, and it is going to be equal to S of the system plus S of the surroundings, or the number of microstates of the system times the number of microstates of the surroundings. Because remember that if we multiply things inside of a natural log, that's the same thing as adding them. Okay, so all of our relationships with entropy start with this Boltzmann definition, where S is KB natural log of omega. And the second law of thermodynamics says that the total entropy, the entropy of the universe, must be increasing. It has to be greater than 0. And then for some specific processes, when a process is reversible, the total energy is equal to 0. When a process is adiabatic, remember that is when dq is equal to 0. When it is adiabatic and reversible, then delta S of the system is 0. These differences are because that reversible systems are always at equilibrium. They're well defined. Remember, we're moving slow enough that we are never out of equilibrium. Adiabatic processes do not. They're not necessarily at equilibrium. But whenever we have an adiabatic and reversible process, then we can know a lot about our system because our entropy is 0. Okay, so we've covered this, that the delta S, the change in entropy of the universe, is going to be equal to the change in entropy of the system plus the surroundings. And we like to call this delta ST is equal to delta S plus delta SR. The delta S of the system, we're going to work through this derivation in a couple of videos, but the delta S of the system can be given by in R natural log of V2 over V1. This is for an isothermal expansion. And we have already defined that the heat capacity at constant pressure is a function of the partial derivative of entropy with respect to temperature. And so if we rearrange this, we can find that delta S is equal to Cp over T dt. Or, I'm sorry, the integral of Cp over T dt. And so this is for our system and allows us to find delta S as long as Cp is constant. And remember that Cp is a function of temperature, but as long as our temperature is not huge, our temperature range is not huge, we can say that it is approximately a constant. Small. Okay, so I was hoping to get you kind of a summary of what equations we're going to be using so that over the next few videos, as I start using these equations, that they're not just coming out of thin air.